Now, so yeah, today it's really great that we've got Zhirong Lin talking about Schrödinger cat states in superconducting resonators. Yeah, so this will be, yeah, this will be great. Come on. So take it away.
Thank you for the introductions, and also it's okay now? Okay,
Yep.
So I'm Zhirong Lin from the Shanghai Institute of Microsystem and Information Technology. It's a kind of institute from the CAS, China. And this talk, actually, I collaborate with some guy like a Pediatrics group from Chalmers who actually provide a device. And also, I was always collaborate with Johnson Chai from Riken, Japan. Yeah, so I'm going to talking about some like a Schrödinger cat state in the superconducting resonator. So yeah, sorry. Okay, so here is a contact. So I would like to starting from the quantum error corrections. So yeah, so everyone knows for quantum computational, you need to have a lot of quantum state, and you need to control the quantum state precisely with high precisions. So this is kind of typical the quantum information logic. But everyone knows there's some loss channel like relaxation defacing to the environment. So, but to run the very deep quantum algorithm, you need to really have a good, I think, many like steps to in order to run some useful algorithm and so on. So typically we need to stop all the quantum errors as we yeah. So but now so to stop the quantum error, so that's why we need the quantum error corrections. So for quantum error correction, you typically need some like if quantum error happens, you need to like coherently control the error and go back to the logic of the qubit. So then the most important thing is you need to have a larger the quantum space, and so then you need to extend the total the physical space. This is the basic idea. You extend the total the physical space, and then you need to real time detect the error. And if you can real time detect the error, you can also do the real time feedback. With this kind of idea, then you can do the quantum error corrections. So to do so, yeah, there are two typical idea. One is everyone knows probably surface code, but for surface code, you are using some near the qubit to protect the logic qubit. And to do so, then you, in principle, you have lots of physical qubit to extend your like quantum state space, and then you have some like logic information and also some error space. But all the error, when error occurs, it just go to error space, but you can coherently control and then mapping to or operating to the correct state. Another idea is like bosonic code. Yeah, for bosonic code, so for bosonic code, we are just employ some like a linear oscillator. With linear oscillator, you have a lot of the here space. With a lot of here space, in principle, you can encode all your information in these Fock states. And you can do a lot of error corrections, and then you in just a simple the oscillator, and then you scale it up. This is the basic idea for bosonic code. And for bosonic code, they actually have many types of the ideas. For example, like a binomial code. For binomial code, you can encode information to 0 and 1. And for example, this is the Fock state 0 and 4. And if there's error happens like photon loss, then for 0 it goes to 3 state, but for 1 it goes to the Fock 1 state. And you just continually monitor the number of the photon. If the Fock state is 1, then you know the error is come from 1. And if it's 3, you know the error come from the 0 have some error. And then you just somehow operating or do some operations to goes to the original like a qubit state. And there's another idea. So today I'm mainly talking about the CAD codes. So for CAD code, you just kind of the mapping your qubit state to like even and odd of the cat superposition of alpha and minus alpha. And I will introduce this one later, but there's also famous like GKP code, which here have a lot of the presentation. And another interesting talk code for like cat-based error question code. I think this is a very good idea, a good example to explain what happens for error question. So in this code, they encode the code information 0 to this one, alpha plus minus alpha. And 1 is I alpha plus minus I alpha. So your correct information is in event parity, but your error information is encoded in the odd parity. So once error happens, for example, if there's 0, you lose a photon here, you just wait 4 times, then it come back to 0 again. So the key point, you can continuously monitor the parity of this like photon state, and then you can count the error. Then you know when you can do the error question. This is very, in my opinion, is very I think very good idea. And recently they already have some quantum error question beyond the break and even point using the bosonic code from here and also from China. And so for the cat code I'm going to talking about is like this. You have the this one is to 0 and 1. So in principle is a coherent state alpha and the superposition of minus alpha. So this is easily to generate it by some like coherent drive path, and is an eigenstate of this operator I. And if there's some error happen, you just wait again. So then you can come back again. This is the basic idea of the. So as long as we can achieve the QND, the measurement on parity, we can detect it in the real time. So this is the basic idea of the cat code. And so to do so, previously for the bosonic code, like in Yale University, they are typically using some 3D cavity. It is a real cavity, so it's not easy to scale it up, but it has some advantage that long the coherence time of the photon of the microwave photon state. And here we're going to talking about some achieve this cat code in the like strict 2D, the chip based. So here is the theoretical analysis and design. So here is our chip. We are using some like called snare. It's a typical is like a fast tunable nonlinear inductance in the terminal of the in the terminal resonator. And actually in this one, you need all the potential we can easily written in this way. And so this Hamiltonian of this resonate terminal snare resonator, we can written in this like this Hamiltonian we call snare resonator. And follow we can simplify it as a Kerr Hamiltonian like this one. And this is we call the Kerr Hamiltonian with this in this way. And this is the linear term, and this is a Kerr nonlinear terms. Yeah. So this is we use this our basic element. And so for the basic idea of this Snell terminal resonator is like this way. So basically it can in a like a Fock state, but if we apply some bias to this Snell resonator, the total potential start to have some unsymmetric terms. And unsymmetric terms introduce some nonlinearity of our Kerr effect. And so if you calculate the resonant frequency, you see the resonant frequency tunable with the flash bias, and also the Kerr term is also tunable from the negative to positive, also with the flash bias. And so in order to so here is our Snell terminal resonator. In order to test the state of the photon here, actually we fabricated a qubit we call transmon qubit, which is capacitive coupled to a Snell resonator, a Snell terminal resonator in O. So the circuit, so in O, this circuit can provide some fast tunable the Kerr coefficient, and it can tune from the negative to positive. And meanwhile, so typically, if we have qubit here, so we have some closed cross Kerr turns to the resonator. But because we can tune the Kerr nonlinearity, in principle, we can ideally tune the Kerr nonlinearity to 0, compensate by this Kerr-tunable effect.
Just a quick question on that. How do you apply the bias to get the linearity?
Yeah.
How do you apply the bias current to the snail?
Yes.
How?
Yeah. Okay. How?
Flux bias for the.
Yeah. So here is our circuit. Yeah. So here actually we have some like we apply the current through here, and it is inductive. So here is we apply current here. Then we can inductive couple like mutual. There's a mutual inductance between here the snare inductance and how.
So that doesn't change your potential, like
yeah.
Suppresses the. It's a different degree of freedom, right?
Yeah.
Adding flux to the.
Yes, we just apply the flux to here, but then this is the good idea for Snell, because here is unsymmetric squid. So because of unsymmetrics, so that when you apply the current here through here, actually the potential because because here the total potential of Snell is like this way. So if you apply current, they will induce some like unsymmetric through this turn. Okay, yeah. And so actually this potential I just calculate this turn with the different like phi e. So yeah, then so for example, if you apply different phi e, then you make the potential, you see some unsymmetric here, and so yeah, so the key idea, the key idea for this experiment is we have the tunable Kerr nonlinearity, and it can be tuned from negative to positive. And another thing is because of qubit, we can like so basically all the 3D cavity experiment. So for example, all the experiment in the Yale group, they using the qubit to operate the photons. So because qubit induce some cross nonlinearity. Cross Kerr nonlinearity, then you can operate in the photons. Otherwise, there's no interaction between photons. But if you introduce the like assistant qubit, it induce the unwanted Kerr nonlinearity. But with this Snell terminal resonator, we can actually compensate this cross Kerr turn. Then you can be a completely Kerr-free point. So then your coherent state can be preserved. I think very ideally can be preserved. So here is the basic idea of evolution under the Kerr nonlinearity. So as I explained before, so the Hamiltonian is written in this way with a linear turn, the Kerr nonlinear turn. So if we prepare a coherent state at the beginning, so it's easily to write in the coherent state under Kerr effect like this way. So this is a Hamiltonian. And so this is the quantum state evaluated at tau. So if we wait sometimes, especially choose the timing, like if timing is equal to like tau 0 over m and tau 0 is 2 pi over k, then we can easily prepare to the m component like a cat state. And the good things for this device is we can switch on and off the coefficient on and off, just apply very fast pulse, and then we can switch on and off. This is very good for this linear resonate. So at the beginning,
sorry, can I just ask about the animation? As
Yeah.
I've been sort of looking at it. So what you're saying is, yeah, there's a time there where you start with a coherent state, and then
Yeah.
you get a superposition of 2 and 3.
And
so is the claim that actually I can superpose as many coherent states around a circle as I like,
Yeah.
as long as I get the timing exactly right?
yeah.
I don't know, in this animation, yeah, we
so
just went past the
you can
2,
stop
right?
anytime as you like. Yeah.
There's one, like, yeah, okay, so I just saw 3, I just saw 2,
Yeah.
maybe I saw 4 there. Yeah.
Yeah. So it
So
depends on when you stop.
So is it the case that the smaller the number, the smaller the number of coherent states that I want to have in the superposition, the longer they're sort of hanging around? So because when I look at this video,
Yeah. Yeah.
I can, like I say, I can see 1, 2, 3, maybe 4,
Yes, yeah,
but
yeah.
5, I
Yeah,
can't see
yeah,
it.
yeah.
Is that because it's too, that's because it's too fast, right?
Too fast. You can see here. So you just so if like tau equal to tau 0 over 5, then
Yeah.
then you see this. So here, if this is a tau over 5, then the timing is already this because n is already n is like inter. So it's easy to, I think we can easily, I will show the details about how to n 2, 3, 4, and then
Right,
we can
okay.
go to 5. I think the idea is basically same, basically
Okay.
same.
Yeah.
Is the idea that it's easier if I start in a much more like big alpha coherent state to prepare like these higher order, higher leg cats?
Yeah, yeah, but then of course the loss become faster for sure. Yeah. Yeah, so then at the beginning, so here is our experiment part. So at the beginning, we just do the nonlinear characterizations. So the basic idea is like this. So in our device, we have qubit. So for a qubit, we can detect the state of the Snell resonate. So for the one tone, we just see the frequency of the Snell resonate. We tune the bias, a kind or flash bias of this Snell resonator. We can tune, and then we start to measure the power, different power dependence of this resonant frequency. We can get the Kerr efficiency, and we tune different flash bias. You can see at some point, then is ideally the frequency. It doesn't depend on the
So the black bits are where the resonant frequency is.
Yeah.
And then the y-axis there is the power, the
Power.
size of the coherent state you want.
Yes.
And
yes.
if there was no Kerr shift, it would be vertical.
Yeah. So, but you see here is a kind of negative and positive, and here is very close to the Kerr-free point. So your frequency doesn't depend on the power or alpha. And the second, so another one we can if your Kerr nonlinearity is large enough, then we can directly resolve the energy level to calculate the Kerr effect. So then if we like higher Kerr nonlinearity, then we firstly is already kind of qubit. Of course, not is a bad qubit, but then we try to using this way we apply the 0 to 1. Of course, then we mapping to 1, and then we also try to search in the omega 1 or 2, and then we found here is the kind of the switching between the fork 1 to 2, and then we just simply calculate the difference between the 1, 2 and the 0, 1. We already get the Kerr nonlinearity, and so then we so we can just tune the external flash bias to change the squid loop. And so here is the measurement result with like 1-tone measurement for the Kerr nonlinearity and 2-tone measurement. Of course, for too small the Kerr nonlinearity, we cannot measure with 2-tone. So we found the 1-tone and 2-tone is matched very. I think the agreement is quite good, and this one is the calculation and simulation part. So we found this Kerr nonlinearity is tunable as what we want in the theory. And then the good thing is you see the Kerr nonlinearity can tune from like -5 megahertz to like 5 megahertz, and there's a very perfect point here where the case exactly 0. And this is what we want, because then the coherent state can be preserved.
And so the Kerr nonlinearity that you're measuring here is the sum of the contribution from the snail and the qubit, is that right?
Yeah, yes.
Yeah, so when it's going through 0, the snail is compensating the qubit.
Yes.
Compensating the transmons inherent.
So then this is the flash bias. So then we can just this is easily tuned by some like pulse and so on. And so another one is to do so we need some way technique like Wegener tomography. And I just get this Wigner tomography from this like parity measurement. Actually, this is from the theoretical part. I just follow their idea. We just have the Wigner tomography do the parity measurement. But in real experimentally, what we do is like here. So no matter which kind of the state we generate, we do this Wigner tomography. For Wigner tomography is like this. So here is we kind of searching the gamma, and we apply. So we apply a pi pulse to our qubit. Very quick pi pulse is very short pi pulse. So in principle, it involve all this difference. So you know for different Fock states, the Rabi oscillation frequency is different because of this stress state. But somehow we are apply very sharp the pi pulse, which actually if you see the frequency, if Fourier transform frequency actually involve all this kind of all this kind of switching. So then no matter the resonate in which kind of the photon state, this pi pulse make the half pi pulse make the G to this G plus E. And then it depends on the number, like parity of your photon in the resonator. So if your photon is in out state, then because you wait like pi over chi, and wait for pi over chi. Then so for the out state, it evolved to here. For the even state, it just after some cycles, you come back, just go back to here, and then you apply another half pi pulse. Then you go to the E state. So then we can just measure. It depends on G and E. We know the parity of your photons, and then so here is we do the Wigner functions for the like alpha equal to 1.4. So we can easily tomography will do the Wigner function for the coherent state, and this is why I think very standard technique used in superconducting qubit side. And then we start to do the main result, like a Schrödinger cat state generation. So at the beginning, we prepare, at the beginning, of course, usually you are in a vacuum state. And then we apply some coherent drive to the coherent state. And wait sometimes, like then this is the very quick flash bias. And then as you know, we have many kind of the state. But when you stop here, then you can see you can have the like a cat state for the two superposition, two alphas, and then we actually finally we do this Wigner tomography. And
sorry, just on that last plot, that simulation there is including the effective loss. Is that right? So
yeah.
Optical.
Yeah.
So it's not a perfect cat.
Yes.
And then the blue regions are negative values of the Wigner function, and the red regions are positive.
Yeah. And then, so for example, it depends on, for example, different timing. We can be able to prepare like a 4-component cat and a 3-component cat, and also 2-components. Yeah. In principle, we can also have like a 5-component, but so then there's some like some problem in our device. In our device, our coherence time is not good. When I get the device from pair, I think the T2 is only one microsecond. This is not good number in the superconducting qubit. But even so, we can get if we measure the fidelity is already like around the 90%, 85 to 90%. So now typically it's easy to get like hundreds microseconds of the T2, or maybe 100 but 50. So then in principle, this kind of idea can reach very high fidelity of the cat state.
But I'm thinking that, I mean, so in order to get the 5 state,
yeah,
you would actually be having tau shorter.
Yeah.
But I think that you would have to have your timing much more accurate.
Yeah,
Is that right?
Yeah.
And then also that
True.
that state may well have more it's not clear to me that the coherence time, it's not clear to me exactly how does the coherence time affect the fidelity of these states.
Yeah.
So
Yeah.
in that higher values, higher superpositions are actually shorter times, right?
Yeah. Yeah.
So potentially they're less affected.
Yeah, that's true. That's true. That's true. So then we need to, so the important thing is, so then if we have very accuracy, the timing, like a pulse controller. So actually here we only can control 2 nanoseconds because of
Yeah.
our because of our DS is not good. But if we have very, very good, and also detection is also important. If you can, yeah.
Yeah, so because it seems between those two things, the threefold symmetry is pretty clear in that Wigner function.
Yeah.
But the fourfold
Yeah, that's
symmetry
true,
is sort
that's
of
true.
less clear, and that's the timing accuracy,
Yeah,
right?
timing accuracy. The timing accuracy is not, we cannot control this one accurately.
Yeah.
But if we have a good controller, then I think it's possible. And this is commercially available.
And it would also be your exact knowledge about what the Kerr shift is.
Yes, that's true. That
Yeah,
exactly,
as well.
that's true. So actually, we are not in a perfect Kerr-free, also because of accuracy of our measurement. Yeah.
So does that mean that you think you're more limited by the coherence time of the qubit here, or is it just the fidelity of the pulse?
I think both. Yeah. So our fidelity of pulse is not precisely let into some error because our rotation is not precisely there. Then we stop it. Yeah.
Does that explain the variation in the fidelity that you're?
Yeah. This is one part. Another one is from the loss of photons. So our actually we even for there's some actually we have some troubles of measure the like dephasing time of the coherent state. So in principle we can measure it, but somehow because because here actually is the coherent state, but we can precisely measure T2 for the Fock state. But coherent state involve lots of the different photon numbers. But for different photon number, actually they have different T1 and T2. So to define, I didn't figure out how to define the T2 for the coherent state. Actually, in the end, we just do some average, of course. But I have no very clear idea about, because so if you just a Fock state, it's easy to measure. You just see the, for example, you know the
That would be
yeah.
For the Fock state. You mean what is the decay? If I suppose if I have 0 plus 1,
Yeah.
what is the rate of decay of that phase, or 0 plus phase shift times 1? What is the rate of decay of that phase shift? That's what you mean by T2 of a Fock state.
Yes.
Yeah, and then you're saying for a coherent state.
Yeah.
It's alpha dependent.
Yeah. So well, I mean, I would have thought for a coherent state, the two things that are important is firstly loss.
Yeah.
And then that's going to move the coherent state.
Yeah.
And then if I had dephasing.
Yeah.
That will preserve the photon number, but expand that distribution. So it'll sort of blow out.
Yeah.
Yeah, I don't exactly know how to
Is it
measure
only
that
loss
time
that's
directly.
like important though? Like
No, so dephasing is definitely important.
it'll also change without.
Yeah,
how
so
many photons does it
dephasing is
have?
like you think that the oscillation frequency of the frequency of the oscillator is taking that coherent state and it's spinning around. And dephasing will be like it speeds up and it slows down. And so if you think about a blob going around in a circle, if it speeds up and slows down, it'll end up distributed along the racetrack instead of being a small blob.
I would assume that having the snail in here, maybe I'm missing something.
Yeah.
I would assume that would be sort of not a very good thing moving forward, because that's going to induce dephasing in the system that you don't have with a normal cavity. So what is the motivation for doing it in this way, actually?
Yeah, that's very good question. So here, so if you have perfect, this squid or snail component introduce some dephasing, and but is can good as transmon. in principle is the same. In principle, the limitation is same as transfer. Actually, we improved the device already, and now. But then the problem is if you remove this Snell component, the resonance is much better. Yeah, it's better than what we. But as I explained, so if you don't have this Snell component, your resonate to operating your resonator like a photon state in the resonator, you need some another qubit, yeah. And the qubit for the qubit part, so you need to, in principle, you kind of swap you can swap some like superpositions of qubit to your photon state. Then you prepare some like yeah, and then the key point is this qubit introduce another this kind of the cross Kerr. And this cross Kerr is not, if you have cross Kerr in your like photon cavity, you always have some K. Even the K is not big, but you always a K. You have K, then your let's say is rotating always, yeah. So but with this nail, we can firstly compensate to the perfect Kerr-free point. This is one advantage. And another advantage is you see we can. If you want to make the swap, actually the like operation speed is much slower. But with this, because here you introduce the nonlinearity directly in your resonate, so you control your nonlinearity directly. So the operation is much faster. So we lose some coherence, but we increase the operation speed for the photon state. Yeah.
And you can tune to a zero curve.
Yeah, zero Kerr.
Which is.
Yeah.
So the plot.
Yeah, so yeah, I think they have some competing, of course. So introduce the Snell, introduce some dephasing, but you can increase the operation speed. So yeah, and also you can go to the perfect Kerr-free point. Yeah.
So on that second point, the perfect Kerr-free point, you're tuning in flux to get to that point. I'm also I'm still kind of confused. The potential that you plotted in the beginning, you're showing sort of again getting back to the current bias. You're biasing the current and tipping the potential.
Yeah.
But in your circuit, you don't have that. So how? You're not actually doing that.
I think the bias current is just a flux tunable.
Yeah.
There's degrees of freedom. There's an external and internal degree of freedom in the square.
So
you're biasing.
So here actually the axis is just the flux. Yeah.
Yeah, but the potential shape goes like this when you bias the squid. It doesn't.
Yeah. So for squid,
How important is it? For engineering this Kerr term, like what you're changing the nonlinear.
Yeah.
That's what you're trying to make it a much more nonlinear.
Yeah.
I don't think you're doing that.
Yeah. So yeah, you're right. For squid, your potential is always symmetric. But this is the like merit of this Snell. For Snell, if you have some bias, because it's unsymmetric component, so it introduce some the different unsymmetric. So that's what. So for the if you are in the squid, you always like a double wave potential. Of course, you change. So then come back to. So this is like for the Bragg is a linear resonator, and for the like squid is always like this. But for the Snell actually because this like potential is different.
But you're biasing in this circuit diagram, you're biasing this device. So therefore you're getting the potential that shifts in this way. That's why you have this kind of effect of the potential where you're actually shaking.
Yeah. That's
not what you're doing in the circuit. You're applying a magnetic field for this sleeve, which is only biasing this portion of it. So
yeah. So the kind of so you see, so actually we tune this one. So what we do is external flux bias. We changing this one. Yeah.
I understand.
Yeah.
Okay.
And this one also induce another potential, the unsymmetric. Yeah. Okay, we can maybe discuss this.
Potential, I think it's it's still periodic, but like there's no like top to bottom current bias.
Yeah.
Like,
And then we try to, this is some simulation. This looks, and this is how we do get this fidelity.
Actually,
And-
sorry, I had a question on these plots. So
Yeah.
when you do the state tomography,
Yeah.
is the state tomography like to make these plots, is this done all in one state? So you've like stopped at some time and then you do the state tomography? You
Yeah.
don't make this up for multiple states?
Yes,
Okay.
yeah. So this is, we prepare the state, we start the state generation here. And
And then
then
you
we-
sample all the points in phase
Yeah,
space.
yeah,
Okay.
Yeah, so each plot takes few hours
Yeah.
or half or even longer, 1 day, something like
Wait,
that.
sorry.
Uh.
If it takes a few hours, then you can't be doing it on the same state, right? You're
Yeah.
sharing
You have to-
multiple states.
So in any kind of tomography, I prepare, I measure one thing.
Yeah,
I need
Yeah,
to
right, okay.
re-prepare and measure a new thing.
so then, yeah, I was wondering like, if you don't have precise control about when you stop it, like, it's in principle, these points aren't like for 48 nanoseconds, right? They're like some
Yeah, yeah.
variation around that.
Yeah,
So that would
yeah.
also add to the
Yes.
fidelity.
Yes,
Yes, but is roughly there, yeah, it's almost there, and then you just did demography, you,
But I just wonder like,
yeah,
would
yeah.
the fidelities have to be higher if you were able to?
Yeah,
like,
yes, yes. So it depends on how kind of the density you want for this map, how many points you want.
Yeah.
Okay.
Sorry, you might have answered this before, but why is the fidelity of the 4 greater than the 3? Like it's about 2% higher. So, like, what's the error bar?
This is the questions, because we cannot control the pulse precisely. So they have some, in principle, of course, the shorter should be better in principle, but we cannot control. But for shorter, the pulse width control have some accuracies worse. So then it's not there's some not good dependence for timing. Yeah, that's the key point.
Was there some notion of like what the error bars look like?
Yeah. And okay, so then we try to show what do we say, the Kerr-free. So as we say, after we prepare the Kerr state, we wait some time. So if you have some qubit or transmon which induce the cross Kerr term, actually your cat is rotating always like this way. But in our case, we tried like 0, 100, and 200s. Our cat state is always here without our cat state is preserved because here is a Kerr-free, our Kerr-free point. So there's no unwanted nonlinear effect. So that's the good merit of our Kerr-free resonator. But of course, again, for this device, the T2 is not good. So still we have we can easily lose the information, but the information is introduced by the photon loss but not due to the Kerr effect. And so yeah, before conclusion, I introduce very short our other progress in my group. So actually we tried one experiment is we tried to make some on-chip controller we call DCSFQ to control a qubit. And so for this one, we be able to on-chip, we generate pulses from this DCSFQ and control the qubit from 0 to 1 with the fidelity 96. It's not good because there are some quasi-particle generation, but we are improving and it's going to 99 now already. And we also trying to, so this is one proposal we are doing. Another one in my group.
so sorry, is that I'm just trying to decode your acronym, but the point about this is cryogenic control
cryogenic
signal.
control.
So you're generating that control for the qubit on chip.
Yes, yeah.
And remind me, what is SFQ?
Yeah, so SFQ is a single flux quantum. So this is the device for SFQ. So you know, for loop of so for superconducting device, they have the two principle is one is the quantize of the flux in one loop. Another one is for Josephson junction, it works like a switch. So in principle, this Josephson junction you can switch on and off to introduce the flux to this loop, and then this one again switch on and off. So because of some torque, we can switch on and off some flux in this loop, and then this loop can go out and out. So with some like, for example, if you have some clock like 1 gigahertz, so then you will generate every 1 nanoseconds, single flux quantum, and so all the pulses, involve 1 flux. So if you integrate the voltage and the timing is, so you typically the pulse length is about 1 picosecond. So each into 1 picosecond, so that's called single flux quantum the pulses. So for this single flux quantum process, we are be able to exciting the qubit with very good accuracy, and in principle, in theory, it can be 99.9 and so on. You can achieve the surface code threshold. But now we still a little bit far. We still have like 3% far. The 3%, we already know the reasons. And the first ideas come from Wisconsin's group, from this Robert McDermott from Wisconsin. But we go some explain further. And now we already know how to precisely control. So our basic idea, I'm not sure it's true like this. If we have very big like 3D integrations. So in principle, we can make a lot of qubit in one chip. Another one is we make this DC SFQ in another chip. And then so 1 qubit with 1 SFQ. And we just using like some multi-pixels control. Then we can easily to control the qubit. And then it's easily scaling up. That's without a lot of microwave cables, without microwave like superconducting qubit. There's a problem now. So then we have a lot of cryogenic controller and with made by superconducting electronics, and we have a lot of superconducting qubit. We integrate them together, and actually we come up with some new idea to read out the qubit also on chip. We have some like shift register, and then we can. So in principle, now for qubit readout, we are using the resonator. For example, 10 qubit, we use the 10 resonator with different frequency. But then in principle, 10 frequency and we multi-pixels frequency to read out the 10 qubit. But you need to get the information immediately after you apply the pulse. But if you have some like shift register, or like you can resist your information on chip in somewhere, and then you just get information at the timing you want. So then you can for the basic idea for like for this qubit multi-pixel is a frequency multi-pixel, and then with this our new like shift register, we can now also have this multi-pixels for timing. So then then I think if then in principle with this and cryogenic control and readout, I think the scaling of the superconducting chip can be much bigger. That's the basic idea. We start this kind of basic to start this kind of research. Actually, yeah, this is the first for qubit control. And another we tried another reason. This is of course we trying to make quantum transducer with the same theme, this surface acoustic wave. So because the surface acoustic wave is you have same frequency for superconducting qubit, and in the chip you have same wavelengths for the optic. So if you see so then it's easy. So it's possible to make, or actually to make some like a transducer from the microwave to optic, because for the superconducting qubit and the surface acoustic wave, you have same frequency, you can change the energy. But for this for optical, you have same wavelengths because of the phase velocity is very small for the sound. Yeah, so the wavelength is matching for in chip with the optic. So that's best way. I think in my opinion, the best system for this quantum transducer. But there was some big problem is usually because to do this surface acoustic wave, you need some spatial film to make this so. but this film easily introduce the loss. If you make qubit inside, your lifetime is like 1 nanosecond or so on. So we make this kind of device in thin film. And actually we already achieved a strong coupling between the so on. Just we actually
Strong coupling between the vibration and the qubit.
yeah, the good way is because of thin film, we can etch this aluminum nitride easily, and then we make qubit on the sapphire. Then we can I think make a good coherence qubit on sapphire, and then we make surface acoustic wave here. So then we can actually achieve the good, and actually not very good, but it's already good enough, the qubit on sapphire and the surface acoustic wave. Then we can actually, we already achieved strong coupling. We can also kind of
How strong? What is the G?
G is like 3 makers.
Yeah.
3 makers, and but the loss is less than 1 makers. It's not perfect, but yeah, at least it's easy. Yeah, another way is you need to use the flip chip. That's more complicated. But here we just in one chip we can achieve 2. And another one is we are always trying the traveling wave parametric amplifier with like 2,000 junction junctions. And yeah, this is our best devices. We actually here we have like 2,000 junction junctions, and every 3 junction we have some like resonance matched. This actually have LC resonator here, and we are be able to achieve the gain is about 3.5, like almost like 5 gigahertz. But of course they have some dead like stop band here which cannot be used. So I think it's compatible with the traveling parametric make in MIT Lincoln Lab. Yeah. So yeah. So here is a conclusion. I think the key point is a Kerr-tunable, the nonlinear resonator, and as you say, the fidelity is still limited by like dephasing and also by the precisely control process. But yeah, that's it. So yeah, and so so you see the paper in this Nature Communication, and it's supported by some funding, and yeah, so yeah, thank you. Yeah.
Thanks very much. I should have said at the beginning, we're very lucky that Zhirong is visiting Sydney at the moment. And I should also have framed it that we're hearing a bit about experiment, often the theory talks. But I think it's really good for us to hear about how quantum error correction is getting implemented in the laboratory. Are there any questions? There's been some interrogation as the talk's gone on. Are there any questions?
Besides like this, the snail, like, are there any other elements that could give me this sort of like tunable nonlinearity? Or is it kind of like, is this the least complicated thing that could actually give me like a K that goes to 0 and then like some value? Like I can't think of a squid or like an asymmetric squid or something.
Yes. And actually, yeah. So in this Michel developed group, they have very deep understanding for this one. So 3 is the minimum you need to achieve this kind of 3 JJ is the minimum you need. They have the same. Basically, they just calculate the potential. Yeah. But
more than like.
Yeah, the calculation is yes. So the calculation is somehow you calculate all the potential like this way.
Yep.
But they find 2, 3, 4, 5 something like that, and finally they found 3 is the best element for yeah.
Right.
In principle, you actually here you also have some asymmetric, but too complicated. Then any kind of you can add another EJ because here just 2 types of the junctions, so you have only one parameter beta. In principle, you have other kind of parameter. You can control all kind of potentials. Yeah.
I mean, the reason asymmetry just gives you a nice flat band.
Right.
It doesn't, your frequency is not moving around a lot, so you're not that susceptible to dephasing.
Right.
You're still susceptible, but it's
Yeah.
it's not a sweet spot, but that's why they're using it.
Yeah.
Right? So
Yeah.
I see, Santi.
Can I ask I missed something about the DC SFQ converter.
Yeah.
How does that scale with qubits? You need one of those units for every qubit.
So, here is the qubit. Yeah, here is our qubit.
Yep.
And here is our DC SFQ.
And so if I was using this for many qubits, do I need one of those converters for every qubit?
They have they have many different proposals. One is you can have like one SFQ chip for multi-qubit. That's possible, but because the key idea is you need to frequency resonate with the qubit in order to operate it. Then in principle, that means you need to have generated like arbitrarily the pulses. That induce a lot of like you need a lot of complicated circuit for SFQ, and this is much easier. You see, even this chip is compatible, even can be smaller than a qubit. So my opinion is just one qubit with one this DC SFQ is easy because anyway because now is 3 junctions, so you can control one qubit. If you want to control 10 qubit with one SFQ circuit, in principle we have to do some calculation, and you need like 8,000 or 8,000 of qubit junctions, 8,000 junctions. It's possible, and actually is doable, but the 8,000 is too much to make a scalability. So my opinion is 3 junctions for one qubit, and then the good thing is before finally we need some like demands or marks of demand, some like to making is multi-pixel control. So we have one microwave line, and it can control like for example, tens or even thousands, hundreds of these SFQ, just one microwave cables. That's I think the easier way.
So is the trade-off that you need more DC lines though?
Yeah.
Okay,
Yeah,
so you pay the price, like you
Yes,
can get
yes.
away with one microwave line, but you need more DC lines.
Yes,
Okay.
yes, that's true.
Just a comment on this, the DCSFQ, all it does is it takes a signal at the frequency to input it and convert it into SFQ pulses.
Yeah.
So, you need room temperature sources, like in this experiment, if you're just using a room temperature source at X gigahertz frequency to drive it, so it's
Yes.
if you really thought about scaling this in
Yeah.
particular.
Yeah.
It's no different than using an external microwave source.
No, yeah. Let's
Because all you're doing is
Yeah, yeah.
converting the microwave tone in this experiment or the high frequency tone into
Yeah.
a series of SFQ pulses.
yeah.
That's it. So I mean, this in particular is a nice demonstration on chip, but I'm not really sure that it's.
Yeah, we have same considerations, and the key point is, for each one we need some bias, but the good thing is you again, so if you have multi like SFQ devices, actually again you can easily apply some multi-pixels control like a D-Wave. What D-Wave do for this, they have quantum annealer. For D-Wave quantum annealer, they have a lot of, in principle, they have, because of a bias, they have a lot of for example, for their 5,000 qubit, actually they already have a lot of the DC bias and control. But the good thing is for this kind of device, you can using some multi-pixels control the technique here. And yeah, that I think is easier for the multi-pixels control. It's for the cube. Yeah. Then it may be easier. Yeah. No, I don't know. Yeah.
Okay, I think we'll leave it there. I mean, I think if people have specific questions for Zhirong, I should ask them afterwards. I'm sure he'll be happy to chat. Let's thank him again for